Carbon is an extremely versatile element. It's impressive because it has the ability to bond in lots of ways, so it can take many different forms such as diamond, graphite, buckyballs and nanotubes. Carbon has several different allotropes, each with different chemical and physical traits. Basically, different carbon-carbon bonds result in the allotrope having different properties. Diamond, for example, has covalent network bonds. It's not only a girl's best friend, but is very hard and transparent, and because of its lack of free electrons is an insulator of electricity. Graphite isn't quite so romantic. Its two-dimensional covalent bonds mean it's soft, black, and its delocalized electrons make it a good electrical conductor. Carbon nanotubes are a particularly interesting allotrope of carbon. But why is this carbon-based material so exciting to scientists? Well, it could lead to new advances in many different fields, such as nanoelectronics, small and ultra-sensitive gas detectors, health, and even the environment. How would you know if you came across a carbon nanotube? For starters, you wouldn't trip over one, because as their name suggests, they're nano, which means they're tiny. These minuscule carbon cylinders can be centimetres long, but their diameters are 50,000 times smaller than the width of a human hair. These pictures of a single human hair are taken with an electron microscope. As we zoom in, more features are visible. But the magnification needed to see this level of detail is not enough to see a carbon nanotube. What you're seeing here is a clump of countless carbon nanotubes. We can zoom in further and see more detail, but even these spaghetti-like strands are not single carbon nanotubes. Only at the highest possible magnification can we see an individual carbon nanotube. Not only are they super small, but they're also extremely strong and very light. Like graphite, their delocalized electrons make them good conductors of heat and electricity. Plus, their unique structure makes them electron highways. Electrons can move along them extremely quickly at near ballistic speeds. Unlike most carbon allotropes, carbon nanotubes are synthesized artificially using a variety of methods such as arc discharge, laser ablation, and chemical vapor deposition. Nanotubes can simply be thought of as single sheets of graphene rolled into a tube. Depending on how tubes are made or grown means changes to their structures. Different structure gives nanotubes different properties. This nanotube is a good conductor, while this isn't. Often nanotubes are capped with half a buckyball, a bit like this one. Nanotubes can be single-walled, double or multi-walled, giving them different properties again. Now we've explored the basics of carbon nanotubes, let's meet someone who uses them. Lee Hubble is a PhD student at the University of Western Australia. He's researching carbon nanotubes and how they can be used to create vapour sensors or gas detectors that may be helpful in the fight against terrorism.
The ultimate aim of this research is to produce a real-time, low power consumption, highly sensitive and highly selective chemical electronic noise. The main reason we have targeted carbon nanotubes for our research is to utilise their unique electrical and chemical properties. We are currently fabricating chemiresistor gas and vapour sensors and targeting these sensors for the detection of low vapour pressure chemicals. These compounds include nerve agents such as chemical simulants for sarin gas, plastic explosive tagans and explosive residues, which are all of national security concern. The way these sensors work is that we can apply an electrical potential across the electrodes which form the basis of the sensor. The carbon nanotubes are actually connected between these electrodes and we can monitor their electrical resistance. When a molecule of the chemical comes into contact with the surface of the carbon nanotube, it'll interact with the delocalized electron cloud. These events are monitored and can be converted into a measurable signal. This is an ongoing research effort at the Centre for Strategic Nanofabrication, located within the University of Western Australia. Basically, this is a newly emerging science and the sky is the limit.